So we talked about that first key concept, what is a function? This whole course is called functions, so you can guess that we're going to do a lot of that. But now we also want to say, well, how can I describe a function or talk about the space that a function occupies on a grid, on an x and y axis? And describing relations and functions using number sets. We're just going to talk a little bit about the real numbers, but to get to the real numbers, we're going to cover a few other types of number sets. So n denotes the set of natural numbers, which include all positive counting numbers, but not zero. So, you can sort of think of these as the caveman numbers. There's one, there's two, there's three of them. We haven't conceptualized the idea of there being nothing or none of something, which is really abstract. So the natural numbers, the most natural numbers, is the notion of just counting what's in front of you. Okay, so that's 1, 2, 3. They're whole numbers that don't include zero. W denotes the whole numbers. This was a big jump in terms of abstract thinking, the fact that you can have none of something. So when you add zero in, and it may help you to remember that the word whole has that O in there that will remind you of the zero, whereas in natural, there's no O in there, so there's no zero in the natural numbers. That includes the positive counting numbers and zero. So notice that the natural numbers are actually elements of whole numbers. Okay, it's just that whole numbers also have zero. We can move up another level and talk about the integers. So I denotes the set of integers, which include all positive and negative whole numbers as well as zero. So notice again that in the integers we have the whole numbers and we have the natural numbers. They're all in there, but the integers also include now the negative values. Okay, the -1, -2, negative counting numbers. Notice there's no 0.5 or 1.27 or anything like that here. So natural numbers, whole numbers, and integers are all the counting numbers, no fractions, decimals, or anything like that. Once we move into real numbers include all the integers. Okay, so also integers, whole numbers, and natural numbers include all that, but also include fractions or rational numbers. Okay, so numbers where you can put a numerator over denominator, and that includes terminating decimals like 0.25, which is 1/4, or repeating decimals like 0.333333, which would represent 1/3. Okay, so these are fractions or rational numbers. And then also the irrational numbers, like the non-terminating, non-repeating decimals like pi or √2. The idea of a real number is that it can take on any value, 0, 1, 2, 3, or anything between there to an infinite number of decimal places, fractions, rational, irrational, whatever. So real numbers are any number you can conceive of. We are going to talk about imaginary numbers in the next unit, actually. So hang on to your seats, people, because it's not all real numbers in the world. We do have some complex numbers that will include imaginary numbers. But for now, we're looking at natural, whole, integers, and real numbers. Okay, so these are the number sets that we're going to be working with. The domain, so now we're talking about the spaces that the functions can occupy. The domain is the set of all input values or x elements. Okay, so that just means that all the values for x where your relation or function exists, where you can go there and put a point on a curve or point on a line, that's called your domain. So the domain describes the values that are acceptable for your independent variable, x values for which there is an accompanying y value somewhere on your curve. Domains can be communicated in different ways. So you can just describe it in words, you could sketch it on a number line, or you could put it in set notation, okay, where you give the list of numbers or inequality statements. And to create a set, we're going to need to know proper set notation. So I'll show you a few different ways. I'll show you the number line, the words, and the set notation, and we'll practice them. If we look at this number line, it's only the x value, so we're not looking at y values right now because we're just concerning ourselves with domain. I've got a point at 1 filled in, and then I've got this arrow drawn that's going to the right of that. On the number line, we can visualize this as being 1 is included, and then any value greater than 1 is also included, all the way up to infinity. Okay, so this arrow is implying that we're just going to keep going to the right. And notice this line, which is really a connected set of an infinite number of points, implies that any natural or whole or anything number will work in here, specifically any real number, okay, because we can hit any number of values in between 1 and 2, or between 2 and 3, or between 3 and infinity. So in words, we can say that x is any real number, okay, because we are continuous here, greater than or equal to 1. Okay, so 1 is included because this point is filled in, but it also goes to the right. So there's the greater than or equal to 1. Now, if we use set notation, we can actually say a lot more in a lot less space. So we can say capital D, which is the domain, is the set of all x values such that x is an element of the real numbers where x is greater than or equal to 1. Okay, so notice we can break it down into all these different parts. Capital D is your domain, is your equal sign. This little funny squiggly bracket is the set notation, so it's the set of, and then whatever's inside there is being described. We define the variable that we're working with, so the set of all x values. This vertical line is such that, or you might see it as given or given that in other courses like data management. X is an element of the real number, so we define the set that we're putting our variable in. And then here's the condition where x has to be greater than or equal to 1. Okay, so this little bit of notation here says a lot more than all this says. Okay, you just have to know how to read it, and you will be responsible for being able to read aloud and describe and talk to somebody in these terms, okay, so that you can tell me what to write if I'm writing it in class. Okay, so make sure that you're familiar with each part of these. Given the number line, okay, so if we go from -1 to 2, both those points are filled in and they're connected with this filled in line, so we know that it's any real number here. We can use words to say that x is any real number greater than or equal to -1 and less than or equal to 2. Okay, so x has to be bigger than or equal to -1, but also has to stay smaller than or equal to +2. And we can say this using set notation. So again, we say the domain is the set of all x values such that x is an element of the real numbers where, and then here's where it gets kind of interesting. Notice there's a left endpoint or a lower endpoint or a least value, and we're going to put that at the leftmost part, right? So that's going to be our -1 goes to the left. And then our +2, which is the rightmost value, the uppermost value, or the greatest value, goes on the right. And we know that our variable x is going to be found in between here, or on here, or on here. So I'm going to put the x variable right here in the middle between the -1 and the 2. And then the way that we put the notation for the inequality, we say that -1 has to be the leastmost value, so has to be less than or equal to x, which itself has to be less than or equal to 2. The reason we use less than or equal and not just less than is because this circle is filled in. So if this circle at -1 is filled in, then -1 is a possible value that x could be, so we have to include the or equal. Okay? You can read it backwards, sort of, if it helps. Like if you look at it this way, you can say that x must be greater than or equal to -1. So if you read it in the wrong direction, that might also help you make sense of it. But recognizing that the leastmost value, the leftmost value will go on your left, and the uppermost value, the rightmost value will go on the right. And since our x value is found in between them, we'll put our x in between them, and then we'll just be able to say -1 is less than or equal to x, which is less than or equal to 2. Given this number line here, we can do the same idea. We see that it goes from -2 to +3, but not inclusive. You see how these circles, these points have been left open or unfilled in? And if these circles are open circles, then that means that we could get as close to 3 as we want, but we can't actually be 3. Or we could get as close to -2 as we want, but we can't actually be equal to -2. So when setting up our domain, the domain is the set of all x values such that x is an element of the real numbers where -2 is less than x, which is less than 3. Notice I don't get to say less than or equal. The or equal is only reserved for times when that circle is filled in, so we could actually be that value. So notice the difference here, notice that change. We talk about the range. The range is the same idea, only now we're talking about all the output or the y elements of a relation. The range describes all the values that are acceptable for the dependent variable. So it asks, what are all the y values for which there are accompanying x values on your curve? And we can again communicate them in words using a number line or as a set. Your y-axis, we're going to read it from bottom to top. Just like the x-axis, we read it from left to right. Okay, so I'll show you what we're doing there. If we want to use words, again, note that the open circle means that it can't be equal to. It could get really close to -1, but it can't actually be -1. So y is any real number greater than -1. Okay, so now we're going up, so that implies greater than, we're increasing on the number line. And set notation, we can say now instead of domain, we're saying range, so we use the R, is the set of all y values this time, such that y is an element of the real numbers, where y must be greater than -1. Again, can't be greater than or equal because it's an open circle. If we look at example 6, we're given another number line where we're given two parts. Okay, so notice that instead of being between -2 and 1, it's actually less than or equal to -2 and greater than or equal to +1. So we've actually broken the range up into two parts. So if we say that in words, then we'll say, well, y is any real number, and we're saying any real number because we can see that this line implies the infinite set of points, so it's not just integers or whole numbers or natural numbers. And y is any real number greater than or equal to 1 and less than or equal to -2. Okay? If we change that into set notation, then we just say, range is the set of all y values such that y is an element of the real numbers, where y is greater than or equal to 1, so here's our greater than or equal to 1, and y is less than or equal to -2. So there's y being less than or equal to -2 there. So notice because this is two different sets here, that you have had to make two different statements. Okay, whereas previously, even though there's two values, it's one set, so we can reserve just one statement. Okay, a left endpoint and a right endpoint. So notice the difference there. If we want to bring domain and range together, which we will want to do, if I gave you this relation here, and this is in fact a function because it would pass the vertical line test, we're going to use set notation to describe the domain and the range. I want you to think of this a few different ways. So maybe imagine that a big light is shining directly down onto the graph, and where the shadow would drop, that is considered your domain. Okay, so they're all the x values that if you were to look up, you'd find a y value. Okay, so you can imagine that your domain, imagine that you're just a little dude walking along your x-axis, and here I'm walking out here and I look up and I look down and I don't see my function anywhere, and I walk a little further and I look up and I look down and I still don't see my function anywhere, and then suddenly at -2 I look up, there it is, there's my function. So the left endpoint of the domain for this function is -2. Okay, and if I take a couple steps more and I look up, there it is, take a couple steps more, look up, there it is, keep looking, there we go. Oh, as soon as I step out here and I look up, my function's gone. So we can see, again, if you imagine a light shining down, or imagine you're just walking along the x-axis, looking up and down and looking for your function or your relation, everywhere where you can see it, every place where there is a y value that corresponds to where you're standing, that is on your domain. So we can see here that our domain goes from -2 to +4, okay, inclusive because these circles are filled in, and it's any real number because this curve, this line, this continuous value implies that it can take on an infinite number of values between these two. So that's our domain. Range you can picture the same way, only maybe imagine you're climbing up the y-axis as a ladder and you're looking left and right to see if you can find your function anywhere. So notice that until I hit a point of 1, okay, I can't find my function if I look left and right if I'm climbing up this y-axis anywhere. As soon as I hit 1, there it is, I see my function. If I climb up a little more, there it is again, keep climbing, oh, it's still there, keep climbing up to here, oh, there it is. And as soon as I step out of bounds, as soon as I step above 4 and I look left and right, my function is gone. And so my range is that those values where there is a point that would correspond. There is an x value that would go along with that y value. And that's where your function or relation exists. So in this case, the lowest value is 1 and the highest value is 4. And as soon as we step outside that, we've lost our function. So we're not in the range of our function anymore. So for our domain, x such that x is an element of the real numbers, where -2 is less than or equal to x, which is less than or equal to 4. And then our range is y such that y is an element of the real numbers, where 1 is less than or equal to y, which is less than or equal to 4. So again, notice that for the x, we go from lowest to highest, so we go from the left endpoint to the right endpoint. And then notice for the y value, we also go from lowest to highest, so we go from the bottom point, which was 1, to the top point, which was 4. Okay? So that's our domain and range, how it's visualized here. If you're just given a set of points, okay, then it's not any real number per se, because any real number implies all those rational, irrational numbers, and any possible value in between. But here we've got domain of just -5, -2, -1, and 2. So these are the x values that would correspond with those points. And then the range will be the y values or the output values that go along with those. So here, the output value that goes with -5 is +2, so I put that there. And then the output value that goes with -2 is -2, so we put that there. So we're just reaching all the heights or all the y values or all the output values for each and every of these x values. If you're given a table of values, just do the same thing. These are all your input values, -4, -3, -2, -1, so we're just listing them. And then these are the output values that are associated with them. Okay, so the domain and range, if you're not given a continuous function or relation, won't necessarily be an element of the real numbers. It may just be a certain number of integers or whole numbers.